This presentation is one in a series about the Centaur stage configured for the Titan IV launch vehicle. It was prepared by the Analex Corporation for Martin Marietta. There is a handout which you can use when viewing the presentation. There are view graphs and figures and may be useful in getting the details on some of the figures that don't come across quite as well on the TV screen. Actually, this is a first in a series of presentations and is the Centaur Overview. The contents of the entire series is shown on the next figure. This first presentation, the Centaur Overview, will give an overall introduction to the Centaur stage. It will be followed by presentations on structures, propulsion, fluids and pneumatics, avionics, flight software, and ground and launch operations. The ground and launch operations presentation will also cover factory operations. They are individual presentations. You can watch any or all of them, and you can watch them in any order. The presentation you are now watching is the Centaur Overview. We are going to cover 4 topics. First, we'll discuss the history of the Centaur stage dating back to 1958. We'll then cover the configuration of the stage, the ground and launch operations, and the mission sequence and the performance of the Centaur. The first topic then that we're going to discuss is Centaur history, and will begin in 1958. The development of the Centaur stage was started in 1958 and sponsored by the Advanced Research Projects Agency. Later, the development responsibility of the Centaur was transferred to the NASA Marshall Space Flight Center and subsequently was transferred to the Lewis Research Center. The first development flight of the Centaur occurred in 1962. In all, there were 8 Atlas Centaur R&D flights conducted. The first operational Centaur was launched in 1966 and was a successful surveyor lunar lander mission. Since then, there have been 52 successful Atlas Centaur operational flights lasting through 1987. In the mid-1970s, there were 6 operational Titan Centaur flights. Finally, in 1982, the Centaur was being developed for incorporation into the shuttle. Unfortunately, after the Challenger incident, the development of Shuttle Centaur was terminated in 1986. This next figure summarizes the Atlas Centaur flight history. The first operational Atlas Centaur flight was a successful surveyor lunar mission. In all, 7 surveyor missions were launched. This was followed by the launch of the Applications Technology satellite into a synchronous transfer orbit, and the 2 orbiting astronomical observatories into a higher Earth orbit. In all, 4 Mariner interplanetary missions were flown, 3 to Mars and 1 to Venus and Mercury. In the mid-1970s, there were 12 Intelsat 4 communications satellites launched. 4 Pioneer spacecraft were launched in the mid-1970s. The first 2 were Jupiter flyby missions, and the last 2 were Pioneer Venus orbiter probes. 4 ComStar communications satellites and 3 HEO spacecraft were launched in the late 1970s. The Fleet SATCOM satellites were launched to synchronous transfer orbit to provide communications capability for the Navy and for the Air Force. There were 6 launches in all. 9 Intelsat 5 communication satellites were launched early in the 1980s to provide expanded global communications capability for the Intelsat consortium. This next figure presents a history of the Titan IIIe Centaur flights. The first operational flight was with a Helios spacecraft. In all, 2 Helios spacecraft were launched into interplanetary space to the Sun to perform solar observations. 2 Viking spacecraft were launched to the planet Mars. These orbiter landers provided more direct measurements of Mars and its atmosphere. The Viking missions were followed by 2 Voyager launches. The Voyager launches were a flyby of the planet Jupiter and Saturn to get data on the planets, their moons, and their rings. In addition, one of the Voyager spacecraft went on to perform a flyby of Uranus and is now en route to Neptune. This concludes the discussion of the history of the Centaur stage. The Centaur stage configuration is our next topic. The Centaur stage is shown schematically in this figure. The Centaur is manufactured by the General Dynamics Space Division in their Kearny Mesa facility in San Diego, California. Starting at the top of this figure, the Centaur stage avionics are located on the stage forward adapter. The adapter also serves as the space vehicle interface. 6 forward bearing reactors are located between the forward adapter and the payload fairing shown in this location. They provide for load sharing between the Centaur and the payload fairing during flight through the atmosphere. Later during flight, they are separated from the Centaur and jettisoned with the fairing. The main engines, shown here at the bottom of the view graph, are 2 RL-10s supplied to General Dynamics by Pratt & Whitney. Each engine provides 16,500 pounds of thrust. In the launch configuration, they are stowed in the adapter between the Titan and the Centaur stage. The Titan forward skirt is shown at the bottom of the figure. Titan-Centaur separation occurs at the separation joint shown on the figure. During orbital coast phases, attitude control is maintained by a set of small reaction-controlled thrusters. The thrusters use monopropellant hydrazine as a fuel. The hydrazine is stored in bottles in the aft end of the stage. 2 bottles are used per flight. They're shown in this location. There are also helium bottles located at the aft end of the stage. The helium is used to pressurize the Centaur main propellant tanks. The Titan-Centaur payload fairing is shown as the dotted lines here in the figure. A closer view of the Centaur propellant tanks and the fluid systems are shown in this next figure. Here we have the hydrogen tank, and to the right of the screen is the liquid oxygen tank. The Centaur stage has a total propellant load of 45,000 pounds. The fuel is liquid hydrogen and is stored, as I said, in this conical cylindrical tank, which is 170 inches in diameter. The oxidizer is liquid oxygen and is stored here in this elliptical tank, which is 120 inches in diameter. The 2 propellant tanks share a common bulkhead. The intermediate bulkhead is a double bulkhead with a vacuum space between to provide thermal insulation. That bulkhead is shown here as the dashed line on the figure. The tank structure is welded stainless steel. It is a thin-walled monocoque construction that is pressure stabilized. The LOX tank pressure is kept higher than the hydrogen tank pressure to maintain this common bulkhead in tension. The thrust loads of the RL-10 engine are taken up by a thrust barrel, which is a structure located in the oxygen tank, shown here on the figure. The thrust barrel distributes the loads from the engines along the periphery of the aft LOX tank bulkhead. Because of the use of cryogenic propellants in the Centaur tanks must be insulated to prevent the excess boil-off of propellants during pre-launch operations as well as during other phases of the mission. The hydrogen tank is blanketed with a foam insulation and a radiation shield. The foam insulation is used primarily for the ground operations, and the radiation shield is effective in space. The LOX tank is equipped with radiation shields only. This next figure of the hydrogen and oxygen tank provides the details on the internal fluid systems. The tanks are pressurized from the Centaur stage helium supply. 3 pressure transducers, not shown in the figure, but located both in the hydrogen tank and in the oxygen tank, send data to the vehicle flight computer, and the pressurization and vent software determines whether pressurization or venting of the tanks is required. When pressurization is required, helium can be introduced into the hydrogen tank through the helium diffuser shown here on the left of the figure. The helium is introduced through a bubbler ring in the LOX tank when pressurization is required, and the bubbler ring is located in the aft end of the LOX tank. Hydrogen can be vented through a balanced vent system. The hydrogen vent valve located at the forward end of the vehicle permits venting through the balanced vent system. Venting of the hydrogen occurs during orbital coast periods, and the use of the balanced vent system minimizes torques on the vehicle. LOX venting is not required during orbital coast periods. However, when LOX venting is required during powered phases of flight, it is done through the LOX vent duct shown here on the side of the tank. A liquid hydrogen sump is located on the side and bottom of the hydrogen tank at this position, and a LOX sump is located in the bottom of the LOX tank. The Centaur also has an active propellant utilization system to minimize propellant residuals. It consists of a propellant utilization probe mounted in the hydrogen tank, and is shown here, and a propellant utilization probe mounted in the LOX tank. During Centaur main engine burns, these probes sense the amount of propellants remaining in the tanks. This information is sent to the vehicle flight computer, and the propellant utilization software determines the proper engine operating conditions and adjusts the mixture ratio to minimize propellant residuals. This information is then sent to the RL-10 engines, where their mixture ratio is adjusted accordingly. The liquid level sensors shown here in the hydrogen tank and here in the LOX tank are used to sense the liquid level of propellants during fill and drain operations. An overview of the RL-10 engine is shown in this figure. Again, the engine is manufactured by the Pratt & Whitney Company and is supplied to General Dynamics. The RL-10 is an expander cycle engine. Each engine has its own independent turbomachinery and controls and is gimbaled using hydraulic actuators. The vacuum thrust of the engine is 16,500 pounds, and the engine-specific impulse is 444.4 seconds. The engine weighs 305 pounds and operates at a nominal mixture ratio of 5:1. That's oxygen to hydrogen flow. The mixture ratio can be varied during the flight over a range of approximately 11% to minimize propellant residuals. The chamber pressure of the RL-10 is 465 pounds per square inch, and the nozzle area ratio is 61:1. Another feature of the RL-10 is restartable in space. In fact, most of the Atlas Centaur missions required 2 burns of the Centaur. On several of the Titan IIIe Centaur flights, after spacecraft separation, tests were run to demonstrate that the 2-burn capability could be exceeded. On one of these missions, the Centaur performed 7 burns. Another feature of the RL-10 is that it can provide hydrogen gas for hydrogen tank pressurization. This feature is used in the Titan IV Centaur. During Centaur main engine burns, hydrogen tank pressurization is maintained by tapping warm hydrogen gas from the RL-10. This reduces the amount of stored helium required. The reaction control system of the Centaur uses hydrazine as a fuel, and it is shown in this view graph. The reaction control system serves several purposes. First, it provides a low level of thrust for attitude control and stability during orbital coast periods. It also provides a low level of axial thrusts required to settle the propellants in the main tanks prior to each engine burn to assure that there is liquid in the sumps for the main engines. And third, the reaction control system is used after spacecraft separation to maneuver the stage and provide a separation distance from the spacecraft. The reaction control system consists of 12 small thrusters having thrust levels of 6 pounds each. The thrusters are located in modules, 4 of them located roughly around the circumference of the LOX tank. Each module consists of 1 pitch engine and 1 yaw engine. You can see one of those here. 2 of the modules also contain 2 of the axial settling thrusters, as is shown here. The engines use monopropellant hydrazine as a fuel. The hydrazine is supplied through a manifold which circles the LOX tank. Hydrazine is stored in 2 bottles which are supported off the aft end of the LOX tank. Each bottle has a capacity for 170 pounds of hydrazine. The bottles are positive displacement using a bladder. They are pressurized with helium from the Centaur stage helium supply. This figure shows a top view of the Centaur forward adapter looking down on the stage, where most of the Centaur avionics are located. The inertial reference unit, shown here in the figure, maintains an inertial coordinate system for guidance and navigation functions and uses a 4-gimbal gyro-stabilized platform. Moving clockwise, the servo-electronics unit, shown here, contains the power supply for the IRU. The master data unit, shown here, manages and controls the Centaur telemetry. In Quad 1, the battery busing unit, the BBU, provides the Centaur electric power from the main vehicle batteries, which are silver zinc. Up to 3 batteries are provided depending upon the mission. Up to 3 space vehicle batteries are also provided and are located in Quad 3. Antennas are located on both sides of the vehicle. They're shown here on the figure and down here, and include the flight termination system antennas, the S-band telemetry antennas, and the C-band tracking antennas. Antennas on the payload fairing are used during the atmospheric portion of the flight, and after the fairing is jettisoned, a second set of antennas is located on the vehicle. The sequence control unit in Quad 4 contains 96 magnetic latching relays and provides all sequencing commands for the vehicle. The pyrotechnic control unit controls power to all Centaur pyrotechnics. The servo inverter unit contains silver amplifiers that perform Centaur engine positioning. The last major avionics package is the digital computer unit, which is shown here in Quad 3. It contains all the flight software and will be discussed in more detail in the next figure. The flight software is contained in the digital computer unit, which has a 16,000 24-bit word memory. The software performs all of the pre-flight testing functions, guidance, navigation and control, and sequencing. In addition, the software also controls the Centaur tank pressures. The software also controls the propellant utilization system using data from the propellant utilization probes that were mounted in both the hydrogen and the oxygen tank. In the next 2 figures, we will present a brief summary of the stage weight. Here's a basic dry weight summary of the Centaur. The Centaur is slightly over 6,000 pounds in weight, and you'll notice that the structural weight, a little over 3,500 pounds, is a major fraction of the total dry weight of the vehicle. The next figure shows the total weight of the Centaur. The weight of the expended main propellants, that is the liquid hydrogen and the liquid oxygen, is 45,370 pounds. After adding in the weight of the loaded hydrazine, the vented helium, and the residual fluids, the total weight of the Centaur stage is over 52,300 pounds. This concludes the discussion of the Centaur configuration, and the next topic will be the ground and launch operations. This figure shows a transportation flow of the Centaur vehicle in the General Dynamics facility in San Diego, California. It covers tank fabrication in Building 19 through the time it is shipped to the Eastern Space and Missile Center. In Plant 19, the tanks are fabricated and all the in-tank hardware is installed. The tanks are then shipped to the Kearney Mesa facility where they are checked for leakage in the pressure pit. After a successful leak check, the tanks are shipped to Building 5 where assembly of the stage will be done. Systems tests are performed and the stage is then returned to the pressure pit for a last tank integrity check. The next stop is the thermal acoustic test facility. Assembly of the stage is completed, insulation is added, and fit checks are performed. The stage is then moved into the thermal acoustic test facility where a high pressure helium check is performed. The stage is then subjected to an acoustic vibration test at flight levels while operating. A thermal acceptance test is then performed. After a successful completion of all tests, the stage is loaded on a vehicle and transported to the Naval Air Station at Miramar for shipment to the Eastern Space and Missile Center. Shown in this sketch of the range is the skid strip where the C-5A lands, which transports the center to the range. Also shown in the figure are the vertical integration buildings shown here, the solid motor assembly building shown here, and also the Titan Centaur Launch Complex 41. There is also building 27200 shown on the figure, which is the control center for the Centaur. After the delivery of the stage to the skid strip, it is taken to Cell 3 in the VIB. Final buildup is completed and a number of systems tests is performed. The stage is then taken to Launch Complex 41, where it is mated to the Titan core vehicle. Final testing is completed prior to launch. All operations of the Centaur are controlled from Building 27200 when it is on the range in the VIB or at Complex 41. Building 27200 contains a Centaur ground computer, the telemetry ground station, the data station, and operator consoles. Communications between Building 27200 and Cell 3 of the VIB and the AGE building is through redundant fiber optic systems. So far in this presentation, a brief history of the Centaur was given. The overall configuration of the stage was discussed, and finally a brief description of ground and launch operations was just finished. Much greater detail in many of these areas can be found in the other presentations in the series. The next and last topic to be covered here is a typical mission sequence and the performance of the Centaur. A geosynchronous orbit mission will be used as a reference mission to discuss this subject. This figure shows a schematic of the Earth's equatorial plane and the larger final geo-orbit. After launch from Complex 41, the Titan IV burns out suborbitally, and the Centaur first burn completes launch into a low-altitude parking orbit. The first burn of the Centaur consumes about 14,000 pounds of its propellant. The first burn is followed by a short coast to the equator, where the second burn occurs, placing the stage into a transfer orbit. During this burn, the Centaur consumes about 21,000 pounds of its propellant. The second burn in the transfer orbit raises the apogee of the transfer orbit to 19,300 miles, which is the final geosynchronous orbit altitude. The second burn is followed by a long 5-hour coast to apogee, where the third burn is then performed. This burn consumes about 9,000 pounds of the remaining Centaur propellants. The third burn circularizes the orbit at the geosynchronous orbital altitude, and it also provides a plane change so that the final orbit is in the equatorial plane. Using this mission then as a reference mission, we will now look at a typical mission sequence. The sequence of events leading to the separation of the Centaur stage from the Titan is shown on this figure. Launch from Complex 41 occurs with ignition of the solid motors. Stage 1 ignition and separation of the solid motors is followed by payload fairing jettison. Stage 1 burnout is followed by Stage 2 separation and ignition. After Stage 2 burnout, the Centaur is separated. The separation of Centaur from the Titan second stage ends the sequence of events, and occurs at solid motor ignition plus 9 minutes. The first burn sequence, which places the Centaur and its payload into a parking orbit, is shown on this figure. First of all, the bottom line, though, on the figure, and a few of those to follow, is the timeline. This line is the event taking place. At 0.2 of a second after separation from the Centaur, an engine pre-start sequence is initiated. The cryogenic RL-10 engines require a unique cool-down procedure to preclude cavitating of the engine pumps at engine start. First, the propellant tank pressures must be increased to provide adequate net positive suction head for the engine pumps. Then the feed lines and pumps are cooled down by flowing liquid hydrogen and liquid oxygen through them for approximately 12 seconds. Main engine ignition that occurs at 12.9 seconds after separation from the Titan. MES1 is main engine ignition. Main engine cutoff occurs at MES1 plus 206 seconds. Main engine cutoff 206 seconds after MES1. After main engine cutoff, 4 of the settling engines are turned on to maintain control of the propellants by aiding in damping any of the residual propellant slosh. 60 seconds later, 2 of the propellant settling engines are turned off. The parking orbit sequence is now shown on this figure. During the nominal 12-minute long park orbit, the propellants are maintained in a settle mode by keeping 2 of the settling thrusters on during the entire coast period. Some 70 seconds prior to second main engine start, 2 additional settling thrusters are turned on for a total of 4. This ensures that the propellants are properly positioned for the next engine firing. The typical second burn sequence is shown here. This sequence will place this vehicle in a transfer orbit. Again, a pre-start sequence is initiated 68 seconds prior to main engine start. This burn to MECO 2 is 270 seconds long, and it will consume approximately 19,300 pounds of the Centaur's propellants. At main engine cutoff, the 4 settling engines are again turned on. However, the 5-hour-long coast in the transfer orbit precludes maintaining control of the propellants during the entire time. Therefore, 20 seconds after main engine start, the settling engines are turned off and the Centaur and its payload enter a zero-gravity coasting phase. The transfer orbit sequence is shown in this figure. At 20 seconds after the second engine burn, the Centaur reorients to a payload thermal control attitude with a slow roll. It maintains this condition for the duration of the entire coasting period. The transfer orbit is a nominal 5-hour-long period. At 633 seconds prior to the third burn, the Centaur reorients to the third burn attitude. Settling of the propellants for the third burn is initiated 453 seconds prior to main engine ignition using 2 settling engines. The third burn sequence is similar to the second burn sequence as is shown in this figure. The major difference is that the third burn from MES 3 to MECO 3 is 123 seconds. This burn will consume the balance of the Centaur's propellants, approximately 9,000 pounds. A typical spacecraft separation sequence is shown in this figure. First, the Centaur initiates orientation to a separation attitude. This occurs 60 seconds after the third burn. At 275 seconds after the third burn, the payload is then separated from the Centaur. The Centaur then executes a collision avoidance maneuver. This occurs 600 seconds after separation. It uses the settling motors and the reaction control system. The last phase of the mission sequence occurs at separation plus approximately 1,380 seconds when the propellant tanks of the Centaur are depressurized. This figure summarizes the typical performance of the Titan IV Centaur for 3 missions. geosynchronous, a 12-hour elliptical mission, and a 24-hour inclined. The payload delivered to GEO is nominally 10,300 pounds. For the 24-hour inclined orbit, payload weight is 10,700 pounds. And for the 12-hour elliptical, the payload delivered to orbit is 15,500 pounds. It should be mentioned that payload delivery weights are highly dependent upon specific missions and will vary from mission to mission. This concludes the Centaur Overview presentation. Very briefly, we covered the history of the Centaur stage from 1958 through 1987. We discussed the overall configuration of the Centaur, ground and launch operations, and finally a typical mission sequence. Again, there are 6 other presentations in this series as shown on the view graph here. They are standalone presentations and can be viewed in any order. They tend to run 30 minutes to 1 hour in length. I might point out that this series of presentations was prepared in early 1988 and is based on information current at that time.